Alors, bonjour à tous et toutes, chers collègues, chers invités, pour ce premier webinaire de Sciences de la décision, édition pandémie 2020-21. Il nous fait grand plaisir d'organiser cet événement conjointement avec le laboratoire de statistique du Centre de recherche mathématiques et d'accueillir virtuellement Stefan Wager de l'Université Stanford en Californie. Alors, une brève biographie de Stéphane. Donc, Stéphane est professeur adjoint d'opérations information et technologie au sein de l'école de gestion. Il a fait ses études, son baccalauréat en mathématiques et son doctorat à l'université Stanford, cette fois en statistique, sous la supervision de Günther Walter et de Brad Efron, après quoi il a fait un bref stage postdoctoral à Columbia et il est retourné en Californie. Je crois qu'on peut dire facilement que Stéphane est un chercheur étoile. Il a déjà plus de 40 publications à son actif. Il a publié dans les journaux phares de statistiques, notamment le journal JASA, Biometrica, série B, le journal Machine Learning Research. Il est éditeur adjoint de Biometrica et de JASA Théorie et Méthode, donc ça nous fait grand plaisir de l'accueillir aujourd'hui pour parler de Machine Learning for Causal Inference. Alors, juste avant de laisser la parole à Stéphane, je vous invite, si vous avez des questions durant l'exposé, à écrire dans le fil de clavardage. Donc, on va prendre des pauses entre les sections pour répondre aux questions. Et puis sinon, à la fin, je ferai l'historique. Donc, je vous inviterai à ouvrir votre micro et autrement, je pourrai lire les questions. Donc, merci Stéphane, je te laisse la parole.
Thanks a lot, everyone, for being here. Bonjour à tous. And thanks, Leo, for the invitation and the introduction. I have to say, for all these online seminars, I always have kind of this wistful feeling like it'd be, it'd be so nice to be there in person, get to meet all of you, have conversations, longer conversations. Also, of course, Montreal is always a very nice city to visit. This time in particular, I mean, you have no idea how happy I would be to be out there really anywhere else in California, because we have a lot of smoke, as you may know, and it is not so good. But anyways, that being said, there are a lot of things we can't control, but one thing we can choose to do is talk about research. So that's one. Very, very, very happy to be talking with you here today. Like Leo said, the topic of the talk today is machine learning for causal inference. Before getting started on that, I just wanted to, I should probably recognize that sometimes I've told people I was working on machine learning for causal inference, especially say people working in medicine, and they'd give me these weird looks like, surely you're mistaken. Like, those are two things that do not go together. That is not okay. We don't do that here. The reason for this, I think, is that causal inference, we typically associate this with statistics, with very rigorous guarantees and very sensitive scientific applications. Causal inference, that's a set of tools you want to use if, say, you have a new medicine and you want to go through FDA approval to bring the medicine to the market. On the other hand, machine learning, I think the association here is more towards engineering application, heuristic methods that sure work really well in practice and let you build all kinds of cool stuff like robots, but typically methods that come with much weaker guarantees than more classical statistical methods, and that are more empirically driven. And here there seems to be this inherent tension where causal inference is all about rigor and machine learning is all about heuristics and about just getting things to work. Then how could you possibly use both of these tools together? So anyways, I recognize that I recognize that point, and of course, it's a very valid point. If using machine learning for causal inference would involve reducing the amount of rigor required for causal inference, that would, of course, be really bad, and one shouldn't do it. But what I'm going to try to convince you of today is that if done right, it's possible to usefully deploy machine learning methods in a rigorous causal analysis without compromising formal results. And actually, even more than that, in a sense I'll make clear in a few slides, it's sometimes possible to use machine learning methods to develop causal analyses that are more rigorous than what you could get out of more classical, say, linear regression-based methods, and that the analyses more closely reflect the observational study design that kind of was used to motivate the causal inference problem in the first place. So anyways, that's the goal for today. Let's get started. And just to get everyone on the same page, first wanted to just talk about all this in the context of an application. So here, this is from a collaboration I was working on recently. The question was to understand among victims of traumatic brain injury, there's this new treatment, tranexamic acid, that's sometimes administered. And there was kind of interest in evaluating whether when people were given tranexamic acid, whether it actually helped. And in order to answer this question, we had data from TraumaBase. It's a consortium of hospitals in France, in the Paris region. And this is not randomized data, it's observational data. The way this data was collected was that kind of first responders, when the ambulance gets to a traumatic brain injury victim, they measure a bunch of stuff about the patient. Then they record whether they administered tranexamic acid or not. And eventually they record, did the patient kind of leave the hospital alive, or did they not survive? So this is the data. And so again, for every patient, we observe treatment, we observe the outcome, survival, and a bunch of other covariates like cardiac arrest and what was their capillary hemoglobin concentration before they were admitted to the hospital, and a bunch of other stuff. Okay. We want to measure the treatment effect. And of course, in this kind of situation, the first thing anyone would do is to build a 2x2 table. So for each person, you look, did they survive or not? You look at were they treated or not? You fill in this table. And if you look at this at first, you might think, wow, the treatment is horrible. Survival rates among people given tranexamic acid were way worse than survival rates among those who weren't. But then on a closer look, this is maybe not so strange. Hopefully, I don't think I need to explain to anyone here what's going wrong here. This is essentially a problem, and there are many names for this: confounding bias, Simpson's paradox, and so forth. The problem here is this was not a randomized study. The first responders got to choose who they administered tranexamic acid to and who they don't. They presumably prioritized treatment to people who appeared sicker to them when they first got to them. These were people who were more likely to die whether or not you give them tranexamic acid. And so if it looks superficially here, that kind of people getting administered tranexamic acid were dying at higher rates than those who weren't, it's because they were sicker to start with, not because tranexamic acid hurt them. Okay, so far this should be entirely standard. What should we do? Well, of course, we measured all these other covariates like hemoglobin concentration and were you in a cardiac arrest. The hope would be that you should be able to kind of use these covariates to take out the effect of first responders' decision making, and once you control for them, maybe you get a cleaner measure of the effect of tranexamic acid on survival. And how are we going to do this? There are many ways, but I think in many different application areas in science, in social science, and so forth, think by far the most common way of doing this is just to run linear regression. People think it's simple, it's transparent, ready weight software for it. And so with how linear regression works here is you define your outcome Y, say survival, your treatment W, tranexamic acid, and then your 220 some other covariates Xi. You put them all in a regression model, and then you try to predict the outcome. You end up with a coefficient tau on the treatment coefficient, and we're going to interpret this resulting tau hat as a treatment effect estimate. And does this give you a valid estimate of the effect of tranexamic acid on the outcome? Well, the answer's got to be sometimes, right? There are some assumptions under which this works. The first, this is the big one. Let's kind of remember, if we didn't bring in any covariates, we had this Simpson's paradox problem where sicker people were treated. So then that created a confounding effect. We need to assume that the measured covariates X were enough to get rid of this bias problem, and that once you've conditioned on X's, the treatment is as good as random. So we need there to be no unmeasured confounders. Fine. The second, this is kind of baked into the linear regression specification. If you want to talk about a treatment effect parameter tau, you kind of need to assume that the treatment effect is constant. If the treatment effect isn't constant, then there isn't really a treatment effect parameter tau. Okay. And the third, this is one that people don't talk about as much, but it's a pretty big one also. In order to justify this linear regression specification, you need to assume that all these other confounders that we don't even care about really, that are just here to kind of remove confounding bias, we need to assume that they also have a linear effect on Y. And so given these three assumptions, we're good to go. And the question is, how do we feel about these assumptions? I guess different people can have different impressions. Mine at least is 1 and 2. They're big assumptions, but I also understand what they mean. For the first one, the treatment being as good as randomized given X, right? That's the whole thing, that's the assumption that justifies trying to do any causal inference given the data we have here. The fact that the treatment effect is constant, maybe you believe it, maybe you don't, but it's an assumption with scientific content, and it seems like the scientists should be allowed to make this assumption if they want. But the third one is kind of strange. I mean, in asking why do we assume that these confounders X have a linear effect on Y, it's hard to find anyone who ever tries to defend this assumption or claim that it's particularly realistic. For example, I can't possibly see a scientific motivation for making this assumption here. One of our covariates was capillary hemoglobin concentration. And while I don't know much about the science here, I still assume that the way this works is that there's kind of good region of capillary hemoglobin concentration that you want to be in, and if you're too high or too low, then that's probably bad. This is very vague, but it still suggests that you probably having a linear effect of hemoglobin concentration on the outcome just doesn't make sense. So why are people willing to buy this assumption that X has a linear effect on Y? I think a much more common argument is that, well, that's what everyone does and it's simple and we have good methods that use this assumption, and if we don't make this assumption, then what are we going to do? And that's kind of, linear regression is such a simple method that it kind of justifies making this assumption from a practical point of view, even though we don't believe in it scientifically. And that's the point I want to push back against today. When I try to argue that no, actually there isn't a strong methodological motivation for making this kind of linearity assumption if you don't believe in them. And this is where machine learning tools come in. Machine learning methods deployed right can essentially let you get around this linearity assumption without kind of compromising other aspects of the analysis. And something I just want to emphasize is, again, there's a strong case for doing fully non-parametric things and so forth. So that's a valid thing to talk about. I'm not going to go all the way to that point in this first part of this talk. If you want to assume a constant treatment effect, that's fine. All I'm complaining about is modeling aspects of the problem that you don't care about in ways that you don't believe. So anyways, that's the goal of the talk. How can you use machine learning methods to avoid making assumptions that you don't believe in? I should emphasize that a lot of what I'm going to talk about today is not new. These ideas have a long history, 20, 30 years at the very least. A bunch of people have worked on these results, including at Montreal. The number of people who have worked on this is too big to kind of list everyone on one slide. Some names I cannot not name are Jamie Robbins, Mark van der Laan, and Victor Chnozikov. So for the first part of this talk, I'll focus on basic results from this line of work. How at a high level can you use machine learning to estimate causal parameters? And then in the second part of the talk, I'll talk about some newer stuff also around methods for treatment heterogeneity. And this is joined with Susan Aithy, my student Xingwen Ni, and Joy Detrani. So before moving on, I wanted to check, does anyone have any questions? If not, let's keep going. So the complaint here was that we wanted to get rid of this linear specification that governed the relationship between covariates or confounders X and the outcome Y. And how can we do so? At least from a modeling perspective, it's very clear what to do. If we don't think that the X should have a linear effect on Y, let's just not write down a model where the X's have a linear effect on Y. Let's say that Y depends on X through some generic function f of X that we can leave unspecified for now. And then the idea is we're going to try to fit this model and interpret tau as a treatment effect parameter. And this is going to be valid if, like before, treatment is as good as random conditionally on X and the treatment effects are constant. But because you didn't assume linearity on X, then of course you don't need to assume linearity in X. This is easy to write down. Of course, not very useful if you can't estimate tau. So that's what we need to worry about next. And here, even though this is what's called a semiparametric problem, right? Because there's one parameter here, tau. Tau is a parameter, but the rest of the problem here is this function f is non-parametric. So the problem is a non-parametric and a parametric component. This might seem like a harder problem, but it turns out there's a very nice way to approach it that goes back to a simple transformation used by Robinson in 1988. And the idea here is to first define two kind of intermediate quantities. The first here, E of X, this is the propensity score. It's the probability of being treated conditional on your covariate values X. This should hopefully be familiar. In observational study methods, propensity scores crop up all the time. And the other thing we need to define is a slightly more unusual quantity, but also very simple in practice. It's the expectation of Y given X. It's your best prediction of what someone's outcome might be, given that you only know their covariates X. So here M of X comes out to the baseline effect F of X, plus the treatment effect tau times the probability that you're treated given X. And kind of given this notation, we can rearrange the above, you can rearrange this partially linear model here, and you get this instead, where you can identify this treatment effect parameter tau as the solution to a regression that predicts the residuals y minus m from residuals w minus e. And what this implies is if you knew the true m and e, then you could learn tau by just running this univariate regression. So this is nice, but of course, in practice, you may or may not know E. In a randomized trial, you do know E. it's a randomization probability. But in an observational study setting like ours, you usually don't know it. And in practice, you never know M. So you can't just run, this regression directly. You need something more. You need to first kind of correct for these, you need to first estimate these nuisance components. But this suggests a very simple algorithm you could try to deploy for estimating tau. And the algorithm is just, you start by this kind of oracle regression model that comes out from Robinson's transformation, but you recognize that you don't know M and E. So what you're going to do is you're going to first start by learning E hat by solving a prediction problem. Estimate E hat by learning to predict W from X. Similarly, you're going to learn M hat by learning to predict Y from X. Simple enough. These are non-parametric regression problems. We know a lot about non-parametric regressions. And then, given this, you're going to revisit this oracle univariate regression problem that identifies tau, but you're going to plug in M hat for M and E hat for E. And this kind of gives you a closed form solution for tau hat, which takes on this functional form. But just to emphasize, this is what you get by running the univariate regression, but plugging in values for M hat and E. Okay. Nice estimate for tau hat. It's simple, it's justified by Robinson's method, but does it actually work? And here's kind of where this stuff gets really, really nice. It's that it absolutely does work. You can give many formal results in this space, some stronger than others. Here's one result of this type. It's by far not the strongest, but it allows for a very simple statement. And the statement is this. So remember, we're assuming that treatment is as good as random once we control for x's and that the treatment effect is constant. In addition, we're going to need to make modest regularity conditions that really are modest. I'm going to talk about them in a second. And also assume that, right, in steps 1 and 2 of the algorithm above, we had to solve prediction problems where we try to predict y and w from x. We're going to assume that we did pretty well at these prediction problems. In root mean squared error, we're going to assume that we got 4th root rates of convergence. Is this a strong assumption or not? We can talk about it. 4th root rates, it's assuming something. But if you had a parametric model, if you actually assumed the linear specification, then you could get 1 over square root n rates. So you still need to assume pretty good rates, but nothing close to, but you can have an order of magnitude slower rates than you'd get under parametric model. And under these conditions, that is our core assumptions, and that you can solve these prediction problems for M and E quite accurately, we're going to get this tau hat estimate from this residual regression and an associated guarantee that tau hat converges to tau at root n rates, is asymptotically unbiased, satisfies the central limit theorem. And what's more, I'm not going to talk about it much here, but the limiting variance B you get here is essentially what you expect to get out of well-specified linear regression. So anyways, this is the first result. It's simple, and once you understand why it's true, it's maybe not that complicated, but I think at least the first time I saw this, I thought this was amazing, because there's kind of generally this garbage in, garbage out principle in data processing in general, right? If at some point you rely on some components in your data analysis pipeline that are not that accurate, it seems kind of strange to assume that you'd gain accuracy down the road, but that's exactly what happens here. You only get moderately accurate estimates M hat and E hat, but then you can pool them together via residual regression, and what you end up is with a treatment effect estimate tau hat that converges at familiar parametric rate, satisfies the central limit theorem. Essentially, you get everything you would have hoped to get out of parametric modeling without writing down a parametric model. So that's pretty nice. And really the only assumption here we need beyond kind of the core assumptions 1 and 2 we made at the start is that we can estimate M and E at reasonable rates. I mentioned something about modest regularity assumptions. One way to get around those completely is to do a thing called cross-fitting that's very closely related to cross-validation. The idea is when you make these M hat of X predictions here, make sure you don't use the ith observation in training the model that used to make a prediction M hat of Xi at the ith sample. So do this cross-fold prediction. And if you do cross-fold prediction, you can essentially avoid regularity conditions. And given that, you're good to go. That's nice. And the idea is going to be that, okay, once we have this very general, very abstract way of estimating tau, how does machine learning fit in? I haven't emphasized it, but I hope it's implicit. All M hat and E hat are doing is they're solving prediction problems. And all we need to assume about M hat and E hat is that they solve these prediction problems well, and that they get small errors under squared error loss. Now, what are machine learning methods trying to do? They're trying to get small errors. So kind of, if you're optimizing your machine learning method via cross-validation, you're essentially trying to find a method that's optimizing this criterion. So kind of your incentives are aligned with an application of this theorem. And so this kind of really means that throwing in something like a deep net or boosting when estimating M hat and E hat, if that's the thing that optimizes your tested error, then that might be a totally reasonable thing to do here. All right, so that's the main theorem statement. I should also note that maybe some people sometimes react to this by saying like, okay, sure, your guarantees are nice, but this is so complicated. It's a multi-step algorithm. Do we really have to do a multi-step algorithm? I just wanted to say, like, is it complicated or not? It really just depends on what you're used to. And actually, if you look at it in a certain way, linear regression is a special case of this. If you kind of remember your kind of linear algebra, linear regression classes, you might remember that a way to characterize the coefficient for the W coefficient in a linear regression without controlling for x's, you can get this out of a three-step procedure. First, run linear regression of W on the x's alone, then run linear regression of Y on x's ignoring W, take residuals from the two and run exactly the same univariate regression. So in a sense, with this estimator here is just a special case of, is a generalization of linear regression where we replace these two regressions by generic prediction tasks. Now, I should emphasize that there's a lot of subtlety to these statements and that you can kind of go very deep. So what I'm saying here is just kind of it's more of a surface level thing that at least I find helpful in organizing these thoughts. If you're interested in reading more, there's a recent series of paper by Nui and Robbins and co-authors. That's very interesting. But the point I'm trying to make here is that this residual regression, despite building on generic prediction tools, shouldn't be thought of as much more complicated than just running a simple linear regression. So anyways, this is kind of the first thing I wanted to say. And if you have any questions, please don't hesitate to write them in the chat. So the thing we wanted to talk about was how can you measure the effect of a treatment on an outcome under the assumption that the treatment is as good as random conditional on covariates and the treatment effect parameter is constant. And the standard way of doing this is by running linear regression, but linear regression needs a third assumption that is kind of seems extraneous, but people make it anyways, is that the x's, the confounders, also have a linear effect on y. But here we talked about how you can instead use machine learning and the partially linear model to get estimates of tau that are directly justified by assumptions 1 and 2 without this kind of third extraneous linearity assumption, and all you need instead is that you're able to solve the prediction problems for m of x and e of x pretty accurately. So there's one question here. What did you say cross-fitting gets us? What cross-fitting gets us is, in the formal results here, I had this kind of ambiguous statement under modest regularity conditions that, right, it's there, one needs to deal with. And there's some work saying, for example, if you estimate m hat and e hat using the lasso without cross-fitting, maybe these regularity conditions are satisfied. And a lot of the kind of earlier literature on combining machine learning with this kind of partial linear modeling went that route, thinking by 12 papers by Belloni, Chernozukov, Hansen, and that crowd. More recently, I think a more popular approach is that a way to sidestep having to make any regularity assumption at all, essentially, on your predictive method. When I say regularity assumptions, I mean regularity assumptions on m hat and e hat, the learning procedures for those. Making such kind of regularity assumptions, if you want to use the lasso, it's fine, but if you want to use deep learning or boosting, these are just methods that we don't know how to understand, analyze as sharply. So verifying the regularity conditions can be more work. And here the alternative instead is to use cross-fitting. And it turns out that this, in a kind of very nice way, eliminates the need to make regularity assumptions, because you kind of are guaranteed not to have own observation bias, because the ith observation is never used to learn m hat of xi and so forth. And this means that you can use any method you want to get this kind of guarantee. Cool. Any other questions? Can you somehow check the assumption using the residuals from predictions? No. So this is the point where kind of I was like, is this condition good or bad? It's good in the sense that it's flexible and much weaker than what you need for linear regression. It's bad in the sense that it's still an assumption. Not all methods converge at this rate. And how would you check this, right? If you look at kind of your test set error, with infinite data, you're still going to have finite test set error, just because there's some irreducible error you can't predict. Whereas on the other hand, in finite samples, whereas kind of what you care about here is kind of how accurately are you estimating this true function m in terms of m hat, and this needs to satisfy some rate conditions that do go to 0. Now, I assume that probably under very specific conditions, you could try to do stuff like look at how does your test set error vary with sample size and look at the decay rate of that and try to read into that. But I think that would be the kind of thing that's very delicate and gets away from the space where we want to have just very general results that you can apply essentially in generic data generating situations with generic machine learning methods. So in terms of validating this assumption, in practice, I think, as far as I'm concerned, probably the most credible way to do this is just build realistic simulations that you think are of comparable difficulty to the actual data analysis problem you have at hand, and check how well kind of this method does in those simulations, and go based on that. So at least the way I think about this kind of condition is not so much that there's this special threshold at fourth root rate where kind of once you pass the fourth root rate threshold with your machine learning method, then you're just good to go. And in fact, like I said, this is not the strongest result of this type. So even under formal conditions, it might be true that you have a central limit there, even if these fourth root rate conditions aren't satisfied. But the way I think about this result more is at a high level. It gives qualitative alignment with and justification for using general machine learning methods for M hat and E hat, because what this means is that really, in order for this estimator to work, M hat and E hat need to be good under squared error loss. And that's exactly what machine learning methods are going for. So that is a positive alignment. Any more questions? All right. And again, I should emphasize there's a huge literature in this space, and every statement I've made can be refined and made more subtle and discussed. And this result is more one to just get kind of oriented and get an idea of what might or might not work in practice. It's by no means a kind of the sharpest result or minimax result in this space. All right. So anyways, this was our recap so far. So far, it's all been about estimating a constant treatment effect. That's all well and good. Sometimes that's what you want. Sometimes it's not what you want. Sometimes you think different people might respond to the treatment differently, and maybe that's actually what you're interested in. Like in personalized medicine, if you have many different treatments you're considering, you don't just want to know which treatment is better than average. You want to have an understanding of, are there some types of patients who on average benefit more from one type of treatment than the other? And so we want to model treatment heterogeneity. So the next part of this talk is about kind of seeing how we can extend these results on the partially linear model to the case of treatment heterogeneity. So from a modeling point of view, it's kind of clear what to do. Before we had a treatment effect parameter tau. Now it becomes a treatment effect function tau of x. And our task is to estimate this tau of x function. And how is this going to go? First, just to say one obvious thing, if we kind of had a finite number of discrete chunks in which the treatment effect were continuous, we'd know exactly what to do. Just look at each chunk separately, estimate the treatment effect in each chunk using our constant treatment effect estimator from before, and then just go from there. But now the difficulty is that x is continuous, so we're going to need to apply some kind of smoothing, and that's what we're going to talk about now. I also wanted to say just here, I'm writing things down in terms of a model like this, just for simplicity, but you can do everything in terms of kind of a more formal unconfoundedness analysis, like in Rosenbaum and Rubin, and that's what we do in the paper. So if you want to kind of see the details there, it's all in the papers. So anyways, under these assumptions, a first thing to note is that this function tau of x, that you can write it as the difference of two regression surfaces. If I define mu w of x as your expected outcome given covariates at x and treatment assignment w, then tau of x is mu1 of x minus mu0 of x. So that's just true and can be helpful to think about. But now if you're kind of in a machine learning mindset, you might think, I now have a really good idea on how to estimate tau hat of x. It's really easy. Mu1 of x is a conditional response function. I know how to estimate it. It's a prediction problem. Similarly for mu hat 0 of x. So I'm gonna first start by fitting mu hat 1 of x and mu hat 0 of x using two non-parametric regressions. And those are gonna be good estimates, and I'm gonna take their difference and I'm gonna get an estimate tau hat of x. And how could this be bad? But here one should be careful. Just because tau of x is equal to mu1 of x minus mu0 of x, that's true. It doesn't mean that mu hat 1 of x minus mu hat 0 of x for generic estimates mu hat and mu hat 0 gives you a good estimate of tau hat. There are many things that can go wrong. Here's just one kind of particularly vivid example taken from a recent paper by Causal, Secan, Bickel, and Yu, which is in the following setting. Let's say here x is one-dimensional. You have a binary treatment. The treatment is randomized, so everything seems as nice as it could possibly be, except we just happen to have more controls than treated. Okay, so we end up in this picture. And what does data look like? Well, you see the data here. We start by fitting the controls. And we have a huge number of controls. So here it's kind of very easy to understand what's going on. We're going to notice that there's this in-between region, this bump in the middle, where the average response of y in terms of x is higher than elsewhere. We fit mu hat 0 accurately. We're happy. What about for treated units? Well, now we have way fewer treated units. So let's say we're deploying a really good machine learning method that notices there's not enough data to learn more sophisticated representations. You need to go for something very simple. And you actually do something really good. You fit mu hat 1 of x as a line. You did a really good job because you didn't have enough data to do anything fancier. So this seems good. But now what happens when you kind of take the difference between these two functions to get a tau hat of x estimate? It's a disaster. You get a big treatment effect here. Then when you go into this middle zone, you get a small treatment effect, and then you get a big treatment effect again. Because just kind of mu hat 1 and mu hat 0, they were trained using different amounts of data. So then when you take and they were regularized differently, so they kind of learned functions of different complexity. And then when you take their difference, suddenly, bam, you think there's heterogeneity, when actually by eye, it's obvious that there's no heterogeneity at all. So this is no good. We don't want to do this. So is there anything better we can do? And here, again, like I said earlier, a natural thing to want is to build on best practices for constant treatment effect estimation, because kind of what is treatment heterogeneity? Treatment heterogeneity, estimating treatment heterogeneity essentially involves finding regions of the feature space where the treatment effect is roughly constant, and then applying a good constant treatment effect estimation tool in these neighborhoods. So just kind of, and kind of building on this idea, imagine someone told you that you wanted to estimate tau of x at a point. You wanted to estimate the conditional average treatment effect for a specific person with covariance x. And you knew that the treatment effect were roughly constant in a neighborhood n of x. Then we could just use our estimator from before. So that is predict m hat and e hat, and then estimate tau hat by residual regression. The only point is that we no longer think that the treatment effect is constant everywhere. We only think that kind of talking about tau of x, that tau of x is roughly constant in the neighborhood n of x, point little x. So now what we're going to do is, before running this residual regression to estimate the treatment effect, we're going to kind of filter our data locally into the neighborhood n of x and run our analysis there. Simple enough. The question is just, how do we choose this neighborhood function? So here, there are many things you could do. There are classical solutions, something like k-nearest neighbors or kernel averaging. The thing I'm going to talk about next is an approach using random forests that tries to learn a good neighborhood function, n of x, using the data. Any questions? All right. So the goal is to estimate something like tau hat of x using a forest-based method that builds on our good constant treatment effect estimator in the partial linear model. To talk about that, I'm first just briefly going to review random forests. I'm going to go quickly because I assume most of you know what these are, and then go back to the problem of treatment effect estimation. So anyways, let's shift gears just for a second. What's a random forest? Random forests, typically we think of them as a prediction algorithm. We want to predict y from x. No treatment for now. We want to estimate mu of x, the expectation of y given x. And how are we going to do this? Well, k-nearest neighbors is going to draw a circle around x, and its prediction of mu of x is going to be the average of all the data inside the circle. A forest is an average of trees. And what does a tree do? Well, a tree does exactly the same thing as k-nearest neighbors, except it averages data inside of this rectangular shaped region that was kind of adaptively chosen to fit the data. And why do we think this would be a good idea? In 2 dimensions, it looks like these two things are really just the same thing, and that's true. Where there's a bigger difference is in higher dimensions. Let's say you're in 20 dimensions. If you want to draw a ball around a point to do nearest neighbors prediction, the ball is going to have to be humongous before you have any neighbors at all. So it kind of suggests that k-nearest neighbors can't be that good. Whereas what trees can do is if there are some directions that matter, you can have narrow, you have kind of a rectangle as narrow in the directions that matter and wide in the directions that don't. And this can kind of improve power a lot. And okay, so then the way you build these trees is by recursive partitioning. So you're going to kind of recursively, you start with all your data in one blob, and then you're going to step by step try to split the blob in two using an axis-aligned split to always greedily improve the quality of a fit that kind of makes constant predictions within each region separated by these splits. So that's a tree. Of course, trees are good. They're simple. They're kind of unstable because in practice you might worry, like, do you make a split like this or do you make a split like that? And it might be kind of really due to small noise effects, whether you choose this split or that split, and that gives you a completely different tree at the end. And people worried about that for a while, like, how do you pick the best tree? And the idea in random forests is don't worry about that. Actually, if there are different plausible trees, just build all of them. So you're going to get a bunch of these trees. They're all going to make a prediction from U of X. And then what your final prediction is going to be, it's going to be an average of the predictions of all the trees you built. And kind of once we have this idea, then it's natural to kind of really explore the space of all plausible trees. And here kind of different subsampling and other ideas are useful in doing so. So anyways, that's random forest in a nutshell. That's a method that's widely used, makes robust predictions. How does this connect to what we wanted to do? That is, how does this give us something that's like a neighborhood function that we can use for heterogeneous treatment effect estimation in a way that generalizes Robinson's method for the partially linear model? And here, a first step that's very simple but helpful is to just rewrite what it is the random forest does. Typically, we think of random forest as being an average of trees. And what is the prediction made by every tree? It's essentially just the outcome yi. The outcome yi. And it's a weighted average of the outcomes yi, where you kind of get constant weight for everyone who falls in the same leaf as the test point x. And you get zero weight if you fall on the outside. So the prediction made by a single tree is an average inside of a rectangle, and then mu hat is the average of the predictions made by a tree. But now, of course, this is a double sum. You can swap the order of the double sum. And now what you end up with, you interpret the random forest as an average of yi's, a single average of yi's with weights. And these weights, alpha ix, essentially are the average of the individual tree weights, and they capture how relevant the ith training example is to predicting at x. So in terms of a picture, what this looks like is kind of each tree on its own, you're predicting at x using an average of data inside the leaf. Here, the size of the dot captures how much weight is given to each observation in the forest. And what the regression forest does is it averages all these tree weighting functions. And so, for example, these 2 points are always in the same leaf as x, so they get really big weight, whereas these points are sometimes in the same leaf as x, so they get moderate weights, and these points are never in the same leaf, so they get zero weight. So, okay. What we've done now is we've kind of reinterpreted a regression forest as a weighted average of yi's, where these alpha i's are kind of a neighborhood function or a kernel function that is adaptively chosen, but govern the weight of each ith training example to prediction at x. And now we're kind of much closer to the type of thing we wanted for treatment effect estimation. Because remember, what we wanted essentially, it's a method that kind of first filters a neighborhood around a point x and then estimates a constant treatment effect in that neighborhood. And the way we're going to do this is we're going to use these random forest weights as kind of a soft neighborhood function. Kind of the bigger your weight, the more relevant you are to inference at x. Except the way we're going to now predict treatment effects at x is So instead of kind of just trying to predict y from x, we now have a treatment again. We want to estimate the effect of w on y conditional on your covariance x. And the way we're going to do this is using this method we always used before. That is kind of by running residual regression, but instead of running it everywhere, we're going to just run it in a neighborhood of x. And what we mean by a neighborhood is we're going to use kind of the random forest neighborhood function to define this neighborhood. So we're going to estimate tau out of x by running a weighted regression, a weighted residual regression. And in this sense, you can think of forest as giving a data adaptive kernel for heterogeneous treatment effect estimation. Questions? Now, of course, I'm leaving a lot of things unsaid. In particular, here I just kind of talked in a very abstract way of how do you go from a forest in general to making kind of regression type predictions or to treatment, estimating treatment heterogeneity. Now there's another question that asks if in the end what we want to do is to estimate this tau of x function using a forest, how should we pick the splits in the trees? How should we grow the forest? How should we tune the forest? There are a bunch of questions like this. And I'm going to just say very briefly, what we do here is we kind of algorithmically mimic a regression forest, except every time a regression forest takes an average of outcomes in order to kind of predict the expectation of y given x, we replace this with a residual regression that tries to estimate the treatment effect of w on y. So, for example, in the splitting phase, when we want to consider is this a good split, what we're going to do is we're going to run a residual regression on this side, a residual regression on this side, and take the difference in the treatment effect estimates and kind of find a split that captures as much heterogeneity as possible. So almost dogmatically, what we're going to just do is we're going to follow the Bryman's algorithmic blueprint for random forests, but just every time Bryman takes an average of outcomes, you run a residual regression. And that's how you, the resulting algorithm is a type of causal forests, and you can use it for heterogeneous treatment effect estimation. Right. So I have more slides than I have time to go through now. I'm going to share them with them organizers in case you're interested. But the last thing I wanted to say in the remaining minutes is just kind of briefly illustrate how this plays out in the context of an application. So this is, here we're using data from the California Greater Avenues to Independence program. It's a welfare to work program, essentially a program helping people on welfare rejoin the workforce. There was a large randomized evaluation gain. It was found to have a big positive effect. So now GAIN is quite widely, or GAIN is now used in California. But then there was also it's also interesting to ask about heterogeneous treatment effects. Are there different types of people who respond more strongly to this intervention than others? So that's what we're going to try to do here. We have access to 54 covariates, including past income, demographics, and so forth. And to make the problem a little bit harder, we here had 4 experiments from 4 different cities with different randomization probabilities, and we pooled them all. So that now kind of there is a confounding element, and the hope is that this method will be able to deal with that also. So anyways, you can train a causal forest on this data set. You find quite a bit of heterogeneity. So kind of people here would be, this would say that kind of the intervention in the 9 years after intervention advise you roughly $100 extra income per quarter, whereas people here, they're $200 extra dollars per quarter, averaged 9 years post-intervention. So that's a lot of heterogeneity, and you can check, is this real? So here what we did was we kind of took out of bag treatment effect predictions, looked at people who were above or below the median, and then we kind of used the randomization inference to check, did this actually improve your outcomes? And we found that the average treatment effect in the group that was selected by the causal forest was higher than among those who weren't by $80 per quarter. So it's a big treatment effect. So this tells you you can find something. What I'm hoping to show with this picture is that what I've said so far, the methods I've talked about so far can be very helpful if you just want to kind of find heterogeneity and directly use it. But in many applications, you might want to be able to do more also. For example, you might want to be able to validate estimates of treatment heterogeneity. Interpretation is important also, especially if you want to use treatment heterogeneity to guide decision rules. Then it's kind of imperative to have things that are more interpretable and satisfy fairness guarantees, so that kind of the community can engage with them. So these are kind of many questions still that kind of anyone using these methods in practice would have to deal with. So this is by no means the kind of end of the line, but what I just kind of to wrap up, what I'm hoping the main message of the talk is that, so you want to do causal inference in a non-parametric setting. Machine learning methods are very useful for this task. They can be rigorously integrated into a machine learning analysis. There are many, many ways to do this. Like one famous version of this is kind of the double robust methods, pioneered by Jamie Robbins and others, and TMLE from the Vanderlaan group. Here I talked about one way of doing this, using the partial linear model, Robinson's method. This is kind of an example often used by the Chernozhukov group at MIT. And the main point is just that kind of you can directly plug machine learning methods into a partial linear model analysis and get good guarantees. And then I also talked about how to use this idea paired with kind of a random forest type construction to estimate treatment heterogeneity and kind of usefully figure out who are people who might benefit from the treatment more or less. So anyways, that's what we can do. And there's still a lot more stuff to do in the future. And slides are, I'll send the slides to the organizers, and I'll just say for now, thank you, and I'm happy to take any questions.
Alors, merci beaucoup Stéphane pour la super présentation. Donc, on peut prendre des questions de l'audience. Si vous avez une question, vous pouvez soit l'écrire dans le clavardage. Oui, on peut applaudir silencieusement ou à l'aide des boutons. Donc, soit vous écrivez dans le clavardage, soit vous levez la main et puis je vous laisse la parole à tour de rôle. Si ce n'est pas la commune, vous pouvez aussi ouvrir votre micro. Des questions? Parce qu'il va y avoir quelqu'un. Oui, François. Alors la question est dans le clavardage. Stéphane, je te laisse peut-être la lire. Tu veux que je la lise?
So the question is, you have, as I understand it, asymptotic guarantees here. In ML, we often have to deal with medium-sized data. So how do your proposed algorithm deal with guarantees in this medium-sized data setting? I suppose I should read your paper. So there are, here I gave an asymptotic result. There are many types of results in this setting. I think that the sharpest results are by Robbins and co-authors and kind of deriving minimax type results in this space. In finite samples, you can actually get a lot more than what I just wrote down here. So here, the guarantee, you might ask, why do you need the assumption of forth-through rates on both m hat and e hat? The way the proof goes is you just have a term that's like sum of m minus m hat times e minus e hat. And you want that to be small. And what you can do is you can apply Cauchy-Schwarz. And then if you have Cauchy-Schwarz along with these two kind of conditions on m hat and e hat decaying fast enough, then that term is negligibly small. So, and that's by far the dominant error term. So essentially, the finite sample statement is that you get a bias term in this central limit theorem that depends on the product of this and this. And I've just made the assumptions under which this product is asymptotically negligible. Now, I think this also points to where this kind of, if you want to dig deeper statistically into here, where is there more stuff going on? Because now you have this term that's like sum of m minus m hat times e minus e hat. You might think that Cauchy-Schwarz is just a very loose way to bound that, and that would be true. If you want to go beyond that, you need to be able to say more about what is it that m hat and e hat are doing. But yeah, that's kind of, that's the type of question that kind of the result that sharpens this result starts by asking.
Est-ce que d'autres personnes voulaient poser des questions à Stéphane? Oui, Yogendra a une question.
Are the conditions in the theorem guaranteed by local linear regression? So here the question is, under what conditions do we get these forth-through rates of convergence? The answer is essentially, I mean, it's well-known conditions, right? If you're in d dimensions and your function is d over 2 times continuously differentiable, then you're fine. And then methods like local linear regression can get this, or local polynomial regression. So yeah, you can give guarantees of this type. And actually that's where the kind of classical literature on this direction went. To solve the kind of these semiparametric problems, they directly went and assumed that, say, the functions m and e had some number of derivatives, and they just wrote down a very specific algorithm that involved using something like local linear regression for m hat and e hat. And then you can kind of derive guarantees under kind of conditions of the data generating distribution. And the direction the literature has been going more recently is like actually checking that kind of condition on a number of derivatives in real data. It's just very hard to think about. So actually it's much easier to think about just kind of very abstractly. You deploy generic prediction tools in different steps. And then if these tools are accurate enough, you're good to go. And then how do you prove these rate bounds? That's kind of a separate exercise. But for example, yeah, local linear regression is one method you can do. You can use for this. There's a recent paper coming out of Chicago Booth where they kind of wanted to get these forth-through conditions out of deep neural networks, and then they kind of highlighted or outlined a set of conditions under which feed-forward network can get you these rates. So this kind of decouples the problem needing to understand properties of machine learning methods and how you post-process their predictions to get treatment effect estimates. There's another question, continuing my first question, do you have some Rademacher or Pack-Bayes results? I think if you, for that kind of thing, the closest to this is, so in the random forest stuff, not really, but these two other papers here have stuff that are closer to what you're asking about. For example, in this paper, what we do is we talk about, it's a very kind of type of question that's very kind of familiar from the empirical process or the literature. Say you want to find a policy that's kind of a linear thresholding rule. And how can you think about learning a decision rule that has bounded regret relative to the best possible linear decision rule? And what are the best regret guarantees you can get? So I think that's a place to look for that kind of results. And then Another question, do you think that using the difference tau left minus tau right as split rule may exaggerate the dispersion of the treatment effect estimates? That's a good question. The first thing I'll say is that here what we try to do with the forests is just mimic Bryman's regression forest as closely as possible. And what Bryman's regression forests do is they try to find a split that kind of improves model fit. So if you have a model where you make one prediction to the left and one prediction to the right, they're going to try to find a split that minimizes the mean squared error of that model. But by kind of decomposing the square, you can see that this is algorithmically equivalent to if you write y bar L for the average of the outcomes on the left and y bar R as the average to the right, then this is equivalent to maximizing NL times NR times this squared. So that's what regression forests do. And what we're just doing is, like I said, quasi-dogmatically running Bryman's forest, except every time Bryman takes an average, we run a residual regression. So what we're going to do is we're just going to, instead of taking y hat L and y hat R by averaging, we're going to do tau hat L and tau hat R by residual regression, and then split to maximize the weighted difference left times right times tau hat minus tau hat right squared. So that's what we're going to do. Now the question is, does this sometimes overfit to kind of regions where, say you have too few observations on the left, so you exaggerate differences? The answer is yes. There's some work on this in this paper by Athey and Imbens, where they consider this kind of Mallows CP type penalty to penalize splits that create too much variance. Now that I reread this question, I realize it also might have meant something different, which is, this is kind of like an overfitting type question, where if we focus, if we kind of split on tau hat L minus tau hat R, is it possible that we exaggerate the dispersion of the tau hats kind of in a way that kind of, if you first run a linear regression and first run lasso to select what variables to go into a linear regression and then run a regression on those variables, you might exaggerate the spread of the coefficients. That is something to worry about. And that's not something I talked about today, but in the GRF package, everything we do involves subsample splitting. So essentially when we train a tree, I didn't talk about this, we're going to first take two subsamples, train a tree on this subsample, and then kind of put that data to the side, flush fresh data down the tree, and use that to make predictions. So that avoids this overfitting aspect. And then we're going to, because forests involve many trees, we don't just do this once, we do this a bunch of times. So every sample gets to sometimes be in the splitting sample and sometimes in the prediction sample. So we don't waste any data, but we can avoid this kind of overfitting problem. But that's also kind of a big issue, especially with treatment effects often are quite weak and quite subtle, so you don't want to exaggerate them. So that ends up being quite important in practice.
Alors, je crois qu'on va clôturer sur ces remarques. Donc, je remercie tout le monde de votre participation.